talking about, there are two types of K, actually three types that we're going to be talking about. There is K, which we just call KEQ, or the equilibrium constant. There's Kc, which is what you do when you're dealing with concentrations. And there's Kp, which is what you'd use when we are dealing with pressures, okay? And so just to make sure that you kind of get an overview of when you would use which one, KEQ is just the general one, okay? That one can be used for any of them. But Kc, when you do concentrations, concentrations are typically for what types of substances? It's when you have what? It starts with an S. Solutions. Awesome, when you have solutions, okay? But if you have gaseous substances, then typically you're not going to be talking about the concentration of a gas. Does that really make sense? Not really, right? So instead, when you're talking about gases, you're going to talk about the pressure of the gases instead. And so then you would be using a Kp instead of using a Kc where you're dealing with concentrations. So why does equilibrium occur? So the equilibrium position is determined by many factors. It could be, what are your initial concentrations? Where are you starting? Remember that your reaction is going to come to a point where it reaches this, not stopping the reaction, but what happens? Where there's no net change. Awesome, where there's no net change. A lot of people believe that reactions completely go to completion, to the end, to form only products. But that's not always the case. So some reactions are reversible, and they can go back and create more reactants than they have products. And so it depends on what you started with and where your reaction is going to go. What are your outside factors? What's the temperature surrounding it? So there are other things that go into that. What are the relative energies of your reactants of products and your reactants? What's your degree of organization of your reactants and products? It says nature tries to achieve minimum energy and maximum disorder. So what we want is, we really want an exothermic reaction. We want minimum energy, and we want maximum disorder. When we talk about disorder, it's called the entropy of the reaction, and you want the most amount of disorder, okay? And those two things, maximum disorder and minimum energy, are both what actually come together to give you what is called a spontaneous reaction. So we'll talk about that later in the year. So equilibrium is reached when the rate of the forward reaction is equal to the rate of the reverse reaction. So again, we say no net change. Okay? No net change is what we're looking at. So let's first talk about these constants. Chemists express the position of equilibrium in terms of numerical values, and we basically just relate what you end with to what you start with. So we say we relate what to what? Products to reactants. Awesome. Okay? And you always do final to initial. Look at the reaction below, where lowercase a, b, c, and d would have numbers. So maybe it's a 1, maybe there's no number in there, maybe it's a 2, maybe it's a 3 or a 4. What is that called? It starts with a C. Those are the coefficients. And what do you know that the coefficient represents? Yep, coefficients representing moles. And capital A, B, C, and D are simply your substances, whatever your substances are. The equilibrium constant, KEQ, is the ratio of the concentration, we already said, of what to what? Products to reactants. And so if you're saying products to reactants and you wrote this as a fraction, you would have P in your numerator and R in your denominator. Okay? So it says with each concentration raised to a power equal to the number of moles, and the number of moles we get from where again? The coefficients. From your balanced equation, from your balanced chemical equation. Thus, the equilibrium constant expression, or KEQ, takes the form of concentration of products over concentration of reactants. But let's make this, as far as A, B, C, and D, let's do it in that way. Okay, so what that's equal to is, let's start with our products. So it's going to be capital C raised to the lowercase c, which would be your coefficient. Not adding, but multiplied. Capital D raised to the lowercase d. So you're not adding them, you're multiplying the two of them together. Divided by, now we're going to do our reactants, and our two reactants are A and B. So capital A to the lowercase a, and capital B raised to the lowercase b. KQ depends on temperature. It makes sense, because what do we say about temperature? Typically, when you increase the temperature, what's going to happen to the molecules? They're going to move faster, and so your collision rate, you have more collisions that are happening. And so when that happens and the energy of the reaction that takes place, then you're going to get your KEQ to change as well. So for gas phase reactions, it says the units of concentration may either be molarity. If it's molarity, then we're just going to use Kc. Or if it's atmospheres of pressure, then we would use Kp. Okay. The ideal gas equation has been converted into this form, but we'll talk about KEQ being greater than and less than 1 in a second here. So Kp and Kc, it says it's equilibrium constants in pressure or molarity. R is simply what?
Gas constant.
Your gas constant. Awesome. Okay. And if we're dealing with energies here, we're going to end up using atmospheres. If we're talking about our converting these two, we're going to use atmospheres, which is 0.0821 liters times atmospheres per Kelvin mole. Okay, so that's typically the one that we're going to use in atmospheres. And then what do you think your temperature needs to be in? This is our temp. What do you think it needs to be in? Kelvin. And how do you go from Celsius to Kelvin? Add 273. Perfect. So remember that your Kelvin temperature is your degrees Celsius plus 273, just as a reminder. And delta N is your change in, what do you think N stands for? Do you remember this? Moles. It's your change in moles between the products and reactants, okay? It's your change in moles between your products and your reactants. All right, so we're going to use this in just a second here. Try this out. KEQ greater than 1. If you get a value here that ends up being bigger than 1, how did that happen? Was your numerator bigger or your denominator bigger if this value ends up being bigger than 1? Your numerator. And if KEQ is greater than 1, it's favoring the products. If it's less than 1 then, and it's reversed, you have more in your denominator than you do in your numerator, then that means it's favoring the reactants. All right, so let's try this. It says for this equilibrium, they're giving you the reaction, and it says at this temperature, 1,000 Kelvin, K has a value of 4.07 times 10 to the negative 3. It says let's try to calculate what Kp is. Okay, I call this the curtain equation. Everybody say curtain.
Curtain.
So because it's Kp equals Kc RT to the delta N, I call this curtain, okay, the curtain equation. So we're going to say that our Kp is equal to the Kc they gave us, so 4.07 times 10 to the negative 3, times our R value, which is in units of atmospheres, so 0.0821, times our temperature, and our temperature they tell us is 1,000 Kelvin, raised to the products minus reactants. So our products, our total products are, how many moles in total? 3 minus how many reactants? 2. So 3 minus 2, which equals 1. Okay, so we're going to raise it to the first power. So go ahead and plug this calculation, plug this into your calculator. Please make sure you try this. The biggest mistake that people will make is their order of operations. So remember, you need to multiply this first and then raise it to the first power. Easy, because it's to the first power. And then multiply it by the 4.07 times 10 to the negative 3. When you do this, you should get 0.334. Are there units? No. This K has no units, but I like this K more than the K from kinetics. And the reason why is, this one actually makes more sense. When you look at this K, it tells you a lot, okay? Because if this number is greater than 1, what does that mean? You're favoring the products at equilibrium. If this number is less than 1, that means you're favoring the reactants at equilibrium. And so in this case here, what is this telling us? We're favoring the reactants at equilibrium. Okay? That's what that means. To tell whether the products or the reactants are favoring in the following. So a KEQ, 1 times 10 to the second is 100. So is that greater than 1? Yep. Yes, so that would be favoring products. 0.003, reactants. This is 0.00060. That would be reactants. And the last one? Products. Got it. Awesome. Equilibrium with all substances in the same phase. If they're all the same, anybody want to guess what we call it? All the same. Starts with an H.
Homogeneous.
Homogeneous. I love it. Homogeneous equilibria is what we call that. If there are different phases, then guess what you call that? Heterogeneous. You are a genius. Okay. The density of a pure solid or liquid is constant at any given temperature, and it changes very little when your temperature is changed. Because they are constant values, they're incorporated right into your equilibrium constant and not in the expression. So let's underline a couple things here. We're talking about pure solids or liquids, okay? Pure solids or liquids. And we're talking about them being constant, incorporated right into the equilibrium constant, not in the expression. So it actually gets thrown in right into your K, okay? So if you have a solid or a liquid, we're going to leave those out. So we only include gaseous or aqueous species in the equilibrium expression, but realize that the solids and the liquids must be present in order for equilibrium to be established. So keep in mind, it's not that they're not necessary and they're not needed and they're not there, because you will not, in this case, if HBr decomposes, you are not just going to form hydrogen. It breaks up, and when HBr breaks up, it breaks up into hydrogen and bromine, okay? So just keep that in mind. So let's write out what our expressions are going to be. So all we're going to do is KEQ is equal to, and we're going to keep on going around the room here. So KEQ is equal to right in the front of the room here. What I want you to do is I want you to give me the products over the reactants, but raised to the power of the coefficient, okay? Can I start with you?
Yeah.
Okay, so we're going to do concentration of H2, and now can you continue for me?
Yeah.
Times?
Br2
Good.
over 2 HBr
Okay, we're going to do HBr because where does the coefficient go?
at the top.
Squared. Awesome. You got it. Very nice. Okay, that's it. Let's do the next one. Do you want to try the next one? Okay.
SO2
Good. And
power of 2
perfect. Squared. Awesome.
times O2
Nice.
over SO3 to the power of 2.
Nice. Over the concentration of SO3 squared. Okay, next one. Try the next one. This one's tricky though, so be careful with this one. KEQ is equal to, why is it tricky, everybody? There's solids. Perfect. There are solids in there.
Concentration of CO2 squared
Nice.
over concentration of CO squared.
Awesome. So it's CO2 squared over CO squared. Again, because these are solids here, they matter, but not for equilibrium. Okay, so those solids get incorporated right into the K instead. Okay, and then let's go back to the back corner of the room. So what would you say for this one right here? KEQ is equal to, again, no solids and liquids.
Concentration of chlorine.
Good, of Cl2, perfect.
That's it.
And that's it, because that's a solid. Nice. Now, if you were doing pressure, what you would do is, instead for this one, you would do Kp is equal to, and you would write PCO2 squared over PCO squared. So if you're doing pressure, that's the only difference. In this case, we're doing KEQ, which could be either one, concentration or pressure. Okay, and that's basically it for